Folks, welcome to Rational Science. We got a great day today. We're going to be talking about what? Time? What is time? And before we get there, we're going to talk a little bit about one fellow who asked about the bending of light. And it's been on my head for some time now. I had it on my head for several years, really. But this fellow brought it back up, so I've been looking at that situation the last couple weeks, and I still have bad news. I don't have an explanation. I have a description, but not an explanation. Not one that I'm satisfied with, not one I'd give my life for, that kind of thing. And then I'm going to be answering another fellow who's been trying to beat me up on my rope hypothesis and also on how good the establishment is. The establishment is doing so well. We'll find out today, okay? Anyways, let's start with the fellow that requested an explanation to the bending of light. When light goes through a prism, it breaks down into colors, and you can see it bending sharply. It's not a curve. It's really bent, like broken. And then it bends again once it goes, the colors go through the prism, and then on the other side, they bend again. And also, the colors come out. But the question is, not the colors, we're all familiar with that. The question is, why does light bend? Very good question. Okay, and so a fellow says the following. He says, I thought there's finally going to be an explanation as to why light bends. Well, I'm sorry to disappoint you. I don't want to lie to you. I have no clue as of today. Well, I can't say no clue whatsoever. I can tell you something today about it and what to look out for, and maybe that'll help you and myself focus in on what bends light, like you see there, light going through a prism. Okay, that's essentially what we're trying to explain. And he says the bottom right corner picture is the correct one, which is the one he's showing there, right? Light inside the medium should always bend less away from the normal compared to outside the medium. What is he talking about? Well, he's talking about this, which I put out last week, okay? And it's the four scenarios, okay? Light coming from above, in both cases at the top, right? And light hitting the prism from a lower angle. So we have higher angle and lower angle, okay? And the question is, which way does light travel through the prism? And which way does light come out of the prism? And to be honest with you, I don't have the equipment to simulate this, and I haven't found anything to my satisfaction out there, okay? I've seen several videos and pictures that people take, but nobody's looked at this in any detail so that, I can really tell you which one is true. And again, I agree with this fellow that maybe the one on the bottom right is the correct one, but I haven't ruled out any of the others to my satisfaction. Okay, so that's all I'm saying for now. When I see something real, someone doing the experiment for real, with the light, impinging, like, here's the prism. If the light impinges at an angle that is like from above, which way does the light come out? That's the question. Okay, and so here you have two prisms back to back, and they more or less imitate what we would see with a lens. Okay, if you point your white light, right, at a lens, you get the blue on the inside and the red on the outside. That's the main thing I want to show there. And you can see that's what you would see probably, right, if you put two prisms back to back. Okay, because that more or less represents what you see with the lens on your left. Okay, and the question is, yeah, we know the blue one's on the inside. That's a description. The question is why. under the rope model, we're saying that the blue has higher frequency, right? Lower wavelength. I'm sorry, longer wavelength. Did I say that right? No, shorter wave, higher frequency, shorter wavelength, and the red one is exactly in reverse, longer wavelength and lower frequency. So what's the issue here? The issue is we have a description, that's based on, in case of the rope model, on frequency and wavelength. So we have no problem with that. That still doesn't explain, right? That still doesn't explain why light bends like that, right? Remember, you have white light coming in, and allegedly light is made of all these colors. And the question is, what does that mean? What do you mean it's made out of different colors, white light? What are we staring at? Well, what is happening in that world, even if we're not around? As soon as all of humanity dies, it still happens. And so, there's going to be a rainbow, with the after a rain, and the question is, why does that happen? What causes it to happen? And here's a vision of what I showed the other day, but this time I'm going to include that other one, that other angle, the one from above on the left. Okay, so we have the white light coming from the bottom at an angle, and we have the one on the top coming at a greater angle. Okay, and the question is, what do we see on the right-hand side coming out of the prism? And right now, I can't tell you that that's exactly what we would show. As you see on the scene on the first picture that I showed, light might come out the top upwards when it comes out of the prism. And this fellow says no. I think he's right. I think it's no. I can only guess that this is what we have to deal with. But then the question here is, we still have a problem because we have the ropes, of two atoms approaching two atoms in the prism. And we're going to assume there's no other atom between them. These are the last two atoms of air before we touch the prism, so to speak. Okay? And so we're just going to put them in that direction. The question is, if it comes from above, you have a greater angle. Will the red still stay on top throughout the prism and coming out? And I would say that, yes, it does. And the question is why? Because, on the bottom side, you can say, when the white light comes in towards the prism, you can see the angle there. It's a short angle. And you could say, okay, the ropes have the blue ropes, in other words, the ones that have higher frequency, right? They bend first. Okay, no problem. But when they come from above, you still have blue, so to speak, on the bottom side, right? And the angle is greater now. And in fact, you could say that the angle of the red rope, in other words, the one with longer wavelength, longer link length, and shorter and fewer links, right? Now the angle benefits the red one. And the question is, do we still get the red on top and blue on the bottom? So we have a problem because it might not be the angle alone, or angle might have something to do with it, the incident angle of white light. But this is one problem we have to look at, the angle. That's why I want to know if the light coming out of the other side of the prism goes up or down. That's I think important to establish that. Right now I cannot establish that because I cannot find a picture that satisfies me that that I can sink my teeth into and say, okay, yeah, this has been shown to be the case, that light either continues downwards or goes upwards when it comes out. Okay, that one I'm still not convinced of. Okay, that's one of the problems. And here's another issue. And here's two prisms side by side at A. When you go to B, all I did was rotate them a little bit so that they're up and down. And the reason I did that is that I want to treat it like a piece of glass, of thick glass. Okay, and light goes through that thick glass like you see more or less at sea. Okay, and when you do that, according to experience, right, white light coming out of there, if you put two prisms, right, back to back like that or side by side, the white light that comes out parallel to the white light coming in. That's what I'm showing there. Okay, and so if we treat it like a piece of glass, the question is, is that the pattern that we would get? Okay, and so these are the things that I'm keeping in mind for when I analyze this. All I can do is tell you what I'm looking at as far as, why light behaves the way it does. Right now, I'm not even convinced of what light does, let alone how it does it. Okay, so that's where I'm at. I'm being honest here, okay? This fellow raised another issue, couple in fact. He says, why does the top rope have a longer length than the bottom one outside the prism to begin with? Couldn't the bottom one be the longer one instead? Yeah, and I really bit my nails on this one for a long time. Right now I'm showing that the red light, the longer links are on the top and the shorter links are on the bottom. That's what I'm showing there. So the longer links are the red ones, the shorter links are the blue ones. Okay, now that's experience, at least as far as the light going through the prism. The question is the white light coming in. Is it already ordered that way, where the red light is on top and the blue light on the bottom? I mean, is there something like that? Does Mother Nature have that order already? Okay, and this is a good question too. I don't think Mother Nature has that order, but I do want to clarify what the question is, what the issues are. And so just bear with me for a second. Here's a beam of light, okay? We took a chunk of it, okay? So a beam of light comes from the left and it's going towards the right, white light, right? And according to the rope model, okay, this is how we're going to model this, okay? We've got on the top we have the longer links, and on the bottom we have the shorter links, okay? So we have red on the top, right, and blue on the bottom, okay? That's what we're showing here. Okay, so the question now is, under the rope model, any two atoms are physically connected by a rope, okay, an electromagnetic rope that sends torsions or torques in situ, and the atoms receive the stimulus, okay? But the question is the following. You can see that the one on the bottom has a lot more links, and they're all shorter, and the one on top has longer links, okay? But there's only one rope between any two hydrogen atoms, right? And so the question is, if there's only one rope, what we're talking about when we're talking about white light is a bunch of ropes, a bunch of atoms also. In other words, for every two atoms, you have one rope. And so here, let's put another one in between, right? So that's what we're saying. And, we could put some more in between. You could say go from red all the way to blue, with the whole spectrum. The question here is, you have these ropes connecting any two atoms. That means that if you have white light, you're talking about a bunch of atoms that are having each two atoms have a different color or different, wavelength or frequency. Okay, that's what I'm saying. Now that's one possibility. Okay, let's look at another possibility. Okay, here it is. Okay, you have more atoms between two atoms of the ones on top. You might have more atoms on the one on the bottom. Okay, in other words, what I'm saying is, in this case, in this situation, you have different frequencies and wavelength in great measure because you have the torsions going from two atoms which are closer together versus two atoms that are farther apart. And so this is another scenario that we got to look at. Remember, for any small amount, like a centimeter cube of air, you got gazillions of air molecules, let alone atoms, that comprise them, because if we're going to look at the fact that the hydrogen atom is our unit of measure. In other words, it's the atom that constructs all other atoms. If you take oxygen, for example, from air, well, then eight of those bubbles that the oxygen has are comprised of 8 hydrogen atoms. And so here we're trying to make it as simple as possible by saying, look, let's just look at hydrogen atoms. And the question is, do we have, with higher frequency, are the atoms closer together? And the reason I say this is that for the same amount of rope, length of rope, right, we would have to have the atoms closer together, you would think, right, than farther apart. And here again, I'm exaggerating what the picture is exaggerating just to make the point. For a given length of rope, you should have, if you have more frequency and shorter links, the atoms you would think are closer together. Okay, so is this the case? And so these are all the things that I'm considering when I'm talking about, the bending of light when it goes through a prism. And these are all the variables that I'm looking into. It's not an easy problem, believe me. It's quite complex. But just want you to know, where I'm coming from with all this. Okay, this fellow also asked another question, also very important, and he talked about the p orbitals that we discussed last week. That's what the p orbitals look like. He says, how does the p orbital form? Remember, the threads, they weave the atom. The one thread goes through the center of the atom, becomes the proton star from every rope in the universe, donates one thread to the center, and the other one goes around. And he asked the question on whether it has to be the magnetic thread all the time or the electric thread. Electric and magnetic threads are just labels we use to keep with convention. That's it. So there's no specific thread called a magnetic thread, an electric thread. We simply say the one that goes around, we're going to call it, and builds the electron shell, we're going to call it the magnetic thread. Arbitrarily, no reason to call it. If you want to call it electric, that's fine, no problem. And the other one goes through the center, we call it the electric thread. That's it. It's the only reason for that is to keep with convention. So I hope that answers that question at least. But he says, I understand that one of the thread wraps around another one to form the shell, but only applies to the s orbital because it forms a ball. And so this is what I showed. I showed that you have the s orbital and the p orbital. There are gazillions of threads building these two objects, right? And they come together, and when the threads of one go down, they're both going clockwise. Clockwise for you, I think, would be like that. For me, it's like this, okay? Doesn't matter. The point is they go in the same direction, either clockwise or counterclockwise. When one comes down, the other one comes up, and that's why one ball, membrane, that's, the threads are rotating at great speeds around the atom. The electron shell essentially spins, as it's called, right? But this is a real spin. And when one goes down, the other one comes up, and that's why they attach to each other physically. Okay, that's the theory. Okay, and here we want to show you what is out there. This is what if you look up the p orbitals, you'll find that the s orbital is in the center. And the p orbitals, you can say the greenish kind of balloons there, they go through and out the other end. They form that figure 8. Okay, and so if you have many of these, like in that case, you got 6 p orbitals. They go right through the center of the of whatever atom that is, right? So the issue here is, you have a s and a p orbital. What do they really look like? And how are they built, which is his question. How do you build one of these things? And this is our model. Okay, we're saying they're all balloons, but they have this structure, this ball of yarn structure. Okay, and I left a couple there the way they were so that you can see what I'm trying to, what we were proposing here. We're saying that all these are balls of yarns are weaved around by gazillions of magnetic threads. That's one issue. And the other one he asked was, can there be two shells? And, of course, I think there are several levels of shells. They're built from every atom in the universe, from every rope coming to our atom, from every atom in the universe. So it's called gazillions. That's the number. That's the perfect, accurate number, precise number for this, okay? So, yeah, could there be several layers? Yeah, absolutely. I think there are. That's my assumption. Okay, that's part of the assumption for the rope model. But you can see this is, if you had the eyes of Atom Man or God or whoever, you go and see an atom, that's more or less what it would look like. Okay, you would see the p orbitals going, being merged to the s orbital in the center. Okay, so that's the way I envision these. And all I can say is, good questions. All I can tell you is how we propose these atoms to be. Okay, and what can I say? We can't still answer some of the questions. We're investigating. We're trying to reason We're trying to reason it out as best as we can, based on our model. But it's a physical model, and that's what distinguishes it from the quantum model, which is not a physical model at all. It's just math. And so people say, well, Bill, what test can we run? How can we prove it? Yeah, there is no proof for this. This is something you make an assumption because you're trying to understand it conceptually. And if you understand it conceptually, then you can explain many things about how the universe works, especially at the micro level, right? And that's the only purpose of the rope model. Okay? Okay, let's move on to our bozo, our clown. And I think he's a clown because I can't take him seriously. I have to believe that some of the things he says are a joke. So I'm sorry to treat him somewhat facetiously, cynically, but you'll look at his questions, his answers, and I think they're close to ridiculous. Okay, and again, it has a lot to do with the fact that I think he has no idea what science is about. He just essentially goes with what the establishment has taught him over the years, and he just accepts it because on the basis of authority, because this is what they told him, and he just gawks and accepts all of this. Okay, and you can see all the problems that it creates for him. Okay, so let's start with the first one. He says the following. He says, Gaede avoided many of the criticisms of where the rope hypothesis fails. Okay, perhaps he can address them specifically. And the issue here is that I deliberately, during 2-3 weeks that we've been at this, I deliberately avoided answering his questions related to the rope model. Okay. And the reason for that, there's a couple reasons there. The first one is that, he tried to answer it himself, in which case he just gave his interpretation of how the rope model would answer some of his questions. And other times he simply said, the rope model can't answer this without giving any reason why he thought like that. So he's kind of putting words in my mouth, or raising strawmen and saying, you can't answer this question, or this is the way the rope would answer it, and it would be wrong, and et cetera, et cetera. And so that was one issue. But a more fundamental issue here is that, what is physics about? What is science about? And this is where we have a mile at least difference between us. We're not even close, okay? And so here, let's go with that issue. He says, Gaede's model prioritizes rationality. Yeah, it's called rational science, right? Consistent definitions, hopefully, right? If we're going to do science, hopefully we don't do inconsistent definitions, meaning irrational definitions, right? Over empiricism. Empiricism. What does empiricism have to do with science? He says, but physics requires both. And the answer is, no. We don't do any empiricism in science, okay, or in physics. Empiricism will elucidate the nature of the invisible, cannot elucidate the nature of an invisible, intangible entity. You cannot go to the lab. You cannot go to the field or wherever, right? Run a test or run an experiment. Try to observe that which is invisible and intangible. You cannot use your eyes and you cannot use your hands. As far as Mother Nature is concerned, we are all quadriplegic and blind. We can't use any. There's no way to detect the exact nature of what she's using as a mediator for gravity and for light, especially those two, got magnetism, electricity, etc., but especially, light and gravity. And so the question is, what empiricism are you trying to do? What experiment? What are you going to do? Why are you going to the lab? You're not going to detect the mediators because they're invisible and intangible. What part of invisible and intangible don't you understand? And science is rational explanations, so empiricism plays no role in explanations. You just have to explain, what's happening in there, okay? And physics is rational explanations of causes and mechanism. And so the question is, we don't need empiricism for that. And of course, if you have a better definition of science that you can defend without resorting to tradition, authority, say, well, all the mathematicians at the math club voted for it. Yeah, we don't care about that. We ask them a question, they can't answer it, then their definition of science is bogus, right? That's what it is. No, you have to be able to defend your definition of science, definition of physics, and hopefully neither one starts with the study of, okay? Because study doesn't make you, studying something doesn't make you a scientist, okay, or a physicist. If you want to be a scientist, a physicist, you got to do something more than just study. You got to explain, you got to produce results, and the results are not measurement. We don't care about your measurement. We don't care about your equations. We need an explanation of how this universe works because that's what people out there want to understand. Okay. And by the way, hold questions until the end. Okay. So if you have questions on today's lecture or anything related to physics, I'll address them at the end. Okay. Okay. So here we have another issue that he raises, which is precision. He says, science prioritizes models that make precise, testable predictions, matching reality. Okay? That's just a description. No? That's all he said. If it matches reality, it's just a description. Now, the model, that's a different question. What model? Model, you mean like an explanation, like a physical interpretation, like a mechanism. You put a model for a engine, but you have to build the engine. You have to put an engine there so that we can see what you're proposing for your model so that we can build it, right? But that's not what quantum does, or for that matter, relativity. What they do is they have these irrational models. So those are not explanations. But yeah, models are part of science, but precision plays no role. What do we need precision for? Okay, science is not an issue of math, okay? And he says testable predictions. A prediction is only a description without more, right? It's just a description. In other words, if I predict that tomorrow at 2 o'clock there's going to be an eclipse of the sun, right? And it happens, well, my prediction came true. So far, all we have is a description. As soon as you try to explain why to someone, why that happened, now you're talking about the past. You're no longer talking about the future. Now you're explaining. You can only explain a consummated event. In this case, the orbit or, the moon going in front. We have experience. We have theories, explanations from past experience, and you're drawing on that to explain it to someone else. So, predictions are descriptions. That's all they are. And so we don't do descriptions, we do explanations. Predict outcomes with extreme precision. Again, got this idea with precision. What's precision got to do with anything? This has only to do with math. When you talk about accuracy, precision, you're just talking about math. You're not talking about explanations. Provide comprehensive what? Evidence. Evidence is used to persuade, to convince people. It's got nothing to do with science. It's got to do with religion. So never present evidence. I mean, there's a tendency for all of us to put some evidence there to say, look, this is how I got my idea because of this, this, and that. I do that with the rope model. I say, look, if we've always looked at the electromagnetic wave, well, here you have the electromagnetic wave, but it's a physical object, not this, this concept full of vectors and fields, which are only numbers. So this is a physical object. Hopefully Mother Nature runs her shop with objects and not with mathematical concepts, and that's the issue. And he also raises the issue of accuracy. He said physical accuracy in science means what? Matching observations, experiments quantitatively. Yeah, he's talking about quantities. And predictively, again, quantities, predictions, that's all he's got in his mind, not just providing mechanisms. Yeah, we're interested in mechanism. We're interested in explanations. He says, gauge model is not physically what? Accurate. Well, I don't know what that means, okay? Accuracy already implies measurement. You're already talking about math, okay? It's got nothing to do with physics. Accuracy equals math, which is not equal to physics. He says his model cannot be empirically falsified. Hopefully. Hopefully it cannot be falsified, because falsification means you're going to convince someone that it's untrue, according to you. So you're just talking about persuading people and convincing people, okay? So falsification has to do with religion. It's an opinion. And then he says QED, QFT, right? Quantum electron dynamics and field theory, right? Validated to what? Astonishing precision. Who cares? I mean, validated means someone convinced you of it. Okay, that's what validated means. Validation just means that someone took the trouble to measure maybe something or convinced you that we are right. We are totally perfect and precise and accurate. And it's to astonishing precision. Who cares? It's irrelevant, totally irrelevant, your precision, your accuracy. And again, validated just means religion, and precision is math. It has nothing to do with physics. Okay, and you say, well, Bill, that's your opinion. Well, let me give you a little authority here, which people only respect authority, unfortunately, today. But let's get authority to bear. Okay, here's good old Feynman, and he said, physics is not mathematics, and mathematics is not physics. Learn it well from Mr. Richard Feynman, Dickie Feynman there. Okay, so, yeah, don't mix math with physics. One has nothing to do with the other one. Okay, so he says, talks about unfalsifiability. We have this clown. His name was Carl Bozo, and he was a part of the circus a long time ago. He was well respected by the entire circus, okay? And so he came up with this notion that, falsifiability or falsification has something to do with science. And all these people just repeat it without understanding what they're talking about. Because if you're going to talk about falsifying, right, or that you're going to falsify something, falsify to whom? In other words, who's going to believe you? I continue believing that it's the truth, but you say, we falsified it. Well, you falsified it for yourself, not for me. You didn't falsify God for me. I continue believing in God. Or maybe it's the other way around. You falsified that, my idea that God doesn't exist. And I say, hey, I continue to believe that God doesn't exist. Falsification is only an opinion. It has nothing to do with science. And he says, so bgaede is unfalsifiable. No predictions. Yeah, no predictions. We don't do predictions. We don't do astrology here. Threads are invisible, intangible. Absolutely. We can't see them. And here, let me prove it. Proof, evidence. You want proof and evidence? Let me get one of my famous pencil, okay? Here, I'm going to let it go. Okay, if I let go of the pencil, it falls downwards. Okay, we know this. I mean, you can test it at home. Don't believe me. Okay, here it is. We let go of it and just take my hands out. And so the question is, here's the pencil, right? It falls. We know that it falls. And I can't see or touch anything here other than the air, right? If I could do this in outer space, somewhere close to the Earth, and it would also fall to the center of the Earth. And I would not be able to see or touch anything there. So hopefully, anybody who proposes anything for gravity, and especially for gravity, right? Whatever mediator you propose, it had better be invisible and intangible, because that is our experience. If you go to the lab and come back with a theory and say, well, no, I've proven the existence of gravity, which is blah, 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 whatever it is, right? And how do you know? How did you prove it? Well, I was able to touch, I was able to see the mediator of gravity. Well, hopefully you're completely wrong. Okay, you cannot falsify or make truthful the mediator of light. It's invisible and intangible. Deal with it, okay? So that's all I can say. And so, yeah, falsifiable is an opinion, right? Religion, prediction, description, that's what it is. It's talking about a future. And science is about the past. Science is about consummated events that we have to explain. We have to explain what, our experience is out there with things. Science explanation also deals only with the past, and verification is only, belief. Verification just means I verified you or unverified you. What does that mean? Well, I have an opinion. That's all it means. I have a different opinion than you do. Okay, that's what it means, unverify or unfalsify. And yeah, so good old Carr, he had his troupe of clowns there, and all these clowns continued talking about falsification and nonsense that has nothing to do with science, let alone with physics. It has only to do with convincing people, with your belief. Okay, you falsified God, but the other guy continues believing that God exists, and that's it. That's got to do with belief. Okay, he also talks about this. What is it? Action at a distance. Let me get it up here. And he says, bgaede demands physical mediators. Hopefully. Mother Nature, out there, she probably does everything, with some mediator. She doesn't do things by black magic. She's a bitch, but not a witch. Okay, so demands physical mediators, objects for phenomena. Absolutely. In other words, you have to have a physical mediator. QED, QFT, entanglement, for example, rely on spooky action at a distance and virtual particles. Action at a distance is irrational. It's what I call their voodoo physics, voodoo magic. You pinch the doll and the guy has a heart attack, right, or whatever. And you have to explain the mechanism. You can't say, well, every time she pinches the doll, this guy gets hurt, or he feels pain in his back, or whatever. How did she do it? Don't tell me it has happened. That's description. Don't tell me how fast it happened. Tell me how many miles she was apart. Any of that. We don't care about any of that. We just want to know what the mechanism by which she pinched the doll and you got hurt. That's what we want to understand, the mechanism. And that's physics. The other stuff, that math garbage about distance and how much time, and we don't care about that. That has nothing to do with physics. bgaede calls them black magic. Yeah, without mechanism. Absolutely. That's what it is. We call it voodoo physics. Whoever does action at a distance. And that's not real physics. It's voodoo physics. You have to have mediators. Mother Nature does not work by magic. She's a bitch, but not a witch. Okay, so here we have, he talks about particles, and he says particles are excitations of quantum fields. That's what they show. They show a little blob, a little bump in the space-time field, which is a bunch of number lines, but they put a net there that represents the number lines. That's what those are. Those little lines going to crisscross, those are number lines. That's what they are. Number lines. What are number lines? Well, they're just concepts. Mother Nature doesn't use concepts to do her work. These people are saying we vibrate these concepts, these numbers, and we create this little bump that's sticking out there. And we call that a particle. Okay, so he calls a particle, he says it's an excitation, a quantum field, whatever that is. And of course, a field is just a bunch of numbers. It's defined as a value at each point in space. And so all these values, right? And so what he's saying is excitations of numbers, of values, of magnitudes or whatever. And he says mathematical entities describing what? Probabilities and interactions. Yeah, exactly. So these are probabilities. It's all numbers. It's got nothing to do with physics. Okay? What did Richard Feynman says? Physics is physics, math is math. Never the twain shall meet. Right, and that's true. Okay, so here we have a couple definitions. Entity, that which has shape. What are fields? They don't have shape. Fields are not entities. Okay, an entity is a physical object. That's what it is. A shape, synonym for it, object, thing, something, anything, body, structure. All those are synonyms of entity in physics for the purposes of physics, not for ordinary speech. Okay? Mathematics describes, physics explains. That's the difference between them. Mathematics fields can't and don't explain. You can't explain with fields because it's a concept, first of all. Second, it's a bunch of numbers. You cannot explain in other words, you cannot give me a physical interpretation using numbers. You cannot use the numbers, say, the numbers pushed against the wall. That's why your house fell down. That doesn't make any sense. Love does not move mountains. Maybe a heart moves mountains, but not love. Okay? Probabilities don't explain either, right? Probability is numbers. What's that got to do with physics? But they keep introducing these physical concepts, right? And they introduce them into physics, and they want to do physics with these concepts. And they say, we understand. No, you described, you can't understand because you haven't explained. That's why. Okay, so he keeps against me, and he says that I reject the wave. Gaede rejects waves as concepts. Absolutely, a wave is a concept. What is it made out of? There you see it. It's electric field, magnetic field. What are fields? Bunch of numbers, right? Values at each point in space. But because made of vectors and fields, right? Because they're made of vectors and fields. What are vectors? Numbers. What are fields? Numbers. They're all numbers. None of that has anything to do with physics. And so, I reject the wave because the wave is not a physical entity. You cannot say the wave did this. Not in physics. In math, you can do whatever you want because, they don't care over there about, physical interpretations. They dismiss it as philosophy or ontology or metaphysics or who knows what. But here we're talking about physics. We want to understand how this universe works from a physical perspective. And hopefully there are physical mediators between atoms, for otherwise we're doing action at a distance, which is what? Witchcraft, black magic, voodoo physics. And we reject particles not because can't interfere, but because quantum particles, what are they? Have magical properties. They talk about quantum particles or mathematical objects. Those are the terms they use. What is that? What's a mathematical object? What is a quantum particle or whatever? And they have to put that adjective quantum or that adjective, mathematical in front of the word object or the word atom. Why? Because they're going to give it some special properties that classical particles don't have. What is a classical particle? Well, here's a classical particle. Let me show you one. It's called a ball. Everybody understand that. Corpuscle, grain of sand, dust, grain dust or whatever. Okay, that's a particle. We all understand the word particle because it's a little ball that does whatever. Okay, and what these people say is, well, it looks like a ball, but it has other properties. It doesn't have the properties that we have in our macro world, where you throw the particle against the wall and it bounces. Sometimes it does when it's convenient for them. Sometimes it doesn't, goes right through the wall when it's also convenient for them. And the way they do it, they say, look, we throw the ball and it turns into a wave at the last moment, or even worse, a wave function. And it's the wave function that goes through the wall. So they give you these idiotic explanations, physical interpretations, but I'm the guy who's in the wrong, right? Okay, so yeah, we reject waves, not because of no shape, but because they're made of vectors and fields. They're numbers. And we don't accept the particles because they have magical properties. Okay, those are the reason that I reject those too. And soon as you define the word object, the word thing, so that we know what you mean by the word thing, then maybe we can have a rational discussion, right? Because now we see where you're coming from. But if you're going to use the words, the definitions that you find in the dictionary or the words of ordinary speech and say, well, an object's that which I can see and touch, or that's made out of particles or whatever, well, those are all irrational definitions. You cannot use those in physics, and that's what they've been using for the last 10,000 years. It's not that I'm defining them all anew, which I am. It's that we've never had a definition. That's the issue. No one has ever defined these words, especially mathematical physics. And again, I always like to say no textbook of physics on planet Earth begins by telling you what an object is, even though you can't do physics without an object. Why has no textbook of physics been written in such a way that it begins by defining the word object? Thing. What is a thing? And nobody has. They begin with force and who knows what. Weight. Okay, here we have our balloon. Okay, so we're going to look at this word field that troubles him so much. We have a balloon, right? And we have a temperature field inside the balloon. Okay, so here's the field. It's a bunch of numbers, no matter what. It's just values. Okay, I just put them in there. And so we have, all these values. That's the field of value at each point in space. We have the space of the balloon inside there. We have all these values. I just put whatever value I wanted in there. It doesn't matter. It's just conceptual so that you understand it. And now we're going to replace that with what's really in there. Is the balloon filled with numbers, values, or is that what we measure? So yeah, we have this field of values that someone measured, and mapped. And here we have what's really in there, which are molecules, right, of air, of nitrogen, who knows what's in there, right? Could be a helium balloon. So we have all these gazillions of atoms in there, or molecules, right, in there. And that's a little different than this, which is, all the numbers, all the values that those things have. And the question is, are these people who talk about fields, are they confusing the numbers with the atoms? Is that what's happening? Values with the molecules or whatever, right? And let's compare them side by side so you know what I'm talking about. See, here on the left-hand side you have the values, and on the right side you have the molecules. Well, the one on the left belongs to mathematics and has nothing to do with physics. The one and that you can call the field. You say that's a field of values. The one on the right is the actual physical stuff that's in there. Okay, and those are atoms and molecules and whatever. So these people are confusing the values at each location and treating them as physical object, replacing the molecules and the atoms. That's what they're doing every time they use the word field. They want to use it as numbers on the one hand and also as physical object, as molecules, as atoms, as locations or whatever, so that they cover both bases, the math and the phys. That's where the problem is. And no, you can't do that. Either a field is what's on the left or a field is on the right. And hopefully it's not the one on the right. The one on the right are known as molecules or atom, and it's the one on the left that has to do with math and has nothing at all to do with physics. Physics, we don't use numbers. We have to explain, and we can't explain with numbers. Okay, here another thing that he raises, the virtuals. Okay, he says H atoms energy level split. An energy level splits? What is an energy level? How can you split a concept? Okay, to vacuum fluctuations. The vacuum fluctuates? I thought the vacuum was nothing. How can the vacuum fluctuate? And the way they do it, they introduce virtual particles. Particles that come in from heaven, I guess. They pop in from the void, they say, and they exist for a very brief, unmeasurable period of time, and then they go back to non-existence, whatever that means. Are we talking about that it turns into empty space, whatever space is? And again, he's saying vacuum fluctuation. So you have the vacuum is fluctuating, and is the vacuum the same thing as the virtual particles? Is the vacuum made of virtual particles? And they say, well, it's made out of energy. Well, what is energy? It's a concept. So we have problem on top of problem on top of problem. And he says, calls popping in and out of existence magic. Absolutely. It's known as magic. What do you call it, if not magic? I thought that is what magic is, when something comes in out of nowhere. Especially, I don't call it magic, I call it black magic. So let's put the word black in there, like saying this is real magic, when something pops in out of the void without any cause or reason, right? Particles tunnel through what? Energy barriers. Well, I don't know what an energy barrier is, because an energy is a concept and it can't be a physical barrier. So to use the word barrier with energy, or to use the word levels, splitting energy levels, it's irrational talk. You can't do anything with energy, because energy is a concept. It means the capacity, blah, 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 blah. So you can look it up. The definition of energy is the capacity. The capacity is not a physical object. You cannot split it. You cannot use it as a barrier. And then he says wave function tunneling. Yeah, with a wave function, I could see that going through the wall. He's got these wave functions traveling all over the place. And they're like ghosts. They can go through walls and they tunnel and whatever. And he said they confirmed it. Confirmed it? You mean they convinced you of it? In fusion reactors. QED, QFT, success. Entanglement, what? Via wave function. Yeah, I can do entanglement with love also, or maybe data. How's that? Information. I mean, what is entanglement? How does it work? Give me a physical mechanism. Don't give me a wave function, a concept. Particle creation, annihilation. You have the positron, the electron there. Annihilation creates new particles. Yeah, so we have this annihilation. That means they turn into what? Into nothing, into space. And by doing so, they create new particles. Yeah, tell me the process. Don't tell me it happens. Tell me what the mechanism is. Quantum scattering wavelength shift is verified precisely. Again, always precision and accuracy, right? And requires photons. Well, is a wavelength the same thing as a photon? Is a photon a little ball? And if so, how do you reconcile it with wavelength? Wavelength is something completely different than a photon. Photons cannot simulate wavelength. Okay, so again, he's got these contradictions. He just puts out words, meaningless words, and he thinks he's explained something with that. And he said, "Oh, we verified it." Yeah, and he says QEDs 10 to the negative 12. Accuracy is the most tested theory. Yeah, we don't test theories. Testing is done by religious people. In science, we don't test anything. We explain so that you understand what the mechanism that we propose is. If you want to go and test it and verify for yourself, convince yourself, that's do it on your own time. Don't do it on scientific time. Okay? The evidence, again, introducing evidence into he thinks it's a court of law or something, is comprehensive. They've enabled what? Technologies like transistors. Technology has nothing at all to do with science. Technology we develop by trial and error. Science is about explaining. What does one thing have to do with the other? Nothing. Okay, then obviously the great famous Tanamura, Japanese guy. Really, he was, there's another group called Morley from Italy, and they did this even before Tanamura, but I guess he doesn't know about that. Anyways, he says, bgaede's particle in two places is cheating. Absolutely. Particles cannot be at two places at once. And if you don't understand that, well, what am I going to talk to you about the rope model if you can't even understand something as simple as this? Even, all the mathematical physicists out there, the mathematicians, they agree that nobody can understand two places at once. But this fellow says, Bill is the only person on earth who says this is cheating. No, hopefully everybody except you knows that it's cheating, okay? So it's the other way around, okay? But Tanamura filmed single electrons building interference over time. Yeah, so what atom did Tanamura do before he did his experiment, right? Because he's got to have a DOE, a design of experiment, before he does his experiment. Otherwise, no one should fund it. When we were in the semiconductor industry, we had to justify the money that was going to be used for a DOE, a design of experiment. And you had to present it to your engineering manager, and he said, how much is it going to cost? Well, it's going to cost $10,000. What's it going to buy us? And so you have to explain, you have to justify the money. These people don't justify anything. They just go directly to the lab and they start saying, oh, we did the experiment and found that we were able to shoot one bullet at a time. Yeah, prove it. How do you prove it? I mean, are you using the Bohr's ridiculous, planetary model of the atom? Is that bead, that little electron bead, the one you shot? So first justify your atom, then we'll find out about whether you handled one electron at a time. First justify your atom. Until you do, you haven't even finished with your design of experiment. Okay, so yeah, Tanamura is assuming the ridiculous and irrational quantum planetary model of the atom. And that's where it all fails. You have to go back to the atom to find out if he really did shoot one bullet at a time. Okay, here's another issue this fellow raised quite a few issues, okay? He says, it fails utterly in explaining, referring to the rope model, quantum scale observations where wave-particle duality, probabilistic outcomes, and field interactions dominate. Phenomena his rope model can't replicate. See, he's just saying that because in his mind, he says, oh, you can't answer that question without contradicting its own rules. And he said, ropes are always taught, so no interference. One thing has nothing to do with the other. Ropes are taught, and we do explain interference very clearly. But let's move on to some other things here. He says quantitative. Well, we can explain the constancy of the velocity of light. We can explain Newton's equation of gravity very easily. We got a couple of videos on that out there, and we can explain the principle of equivalence. We can explain we can explain how a magnet attracts another. We have explanations for a lot of stuff. So when he says I offer no explanations, I don't know what he's talking about. He simply doesn't seem to understand, what we're explaining. That's it. He says contradicts data, and I don't know what data we're contradicting. He says assumes discrete objects. I don't know what he's talking about. Certainly we're not assuming discrete atoms, so I'm not sure what he's talking about when he says discrete objects. But yeah, objects, when we talk about like tables and chairs, we consider them as discrete objects, even though every atom of those tables and chairs are connected to every atom in the universe. Okay, but we treat them as discrete objects. Ignoring wave effects. Well, wave effects are the torsions along the rope, so I don't know what he's talking about there either. And he says fails quantitatively. Again, no idea what he's talking about. He just throws his stuff out. I guess that's why I have to believe he's clowning around. He's got to be a boson. Otherwise, it makes no sense. He says that quantum explains. He says it explains via mechanisms torsions for light, but ignores, that's the rope model, right? Or contradicts vast experimental data. Just a statement, no justification, unsubstantiated. QED, QFT, on the other hand, are conceptually messy, more than messy. They're irrational. It's called irrational, not messy. But provide what? Quantitative predictions. We don't care about that. It's not part of science. Falsifiability, tested in labs. Again, irrelevant. Nothing to do with science. But I like the last one. It says, explain particles. Now, we don't explain particles. We explain what particles do. We don't explain particles. It's like saying, explain a chair. How do I explain a chair? No, I can use the chair to explain something, how, I busted it over your head and why you have a big lump. That I can explain with the chair. But I cannot, hitting the clown over the head, but I cannot explain the chair. I mean, explain your mother. I mean, Jesus. Forces and cosmology. Quantum doesn't explain, and that's widely known, that there are no explanations in mathematical physics. All they have is descriptions. Math can only describe, has no authority, no way of, explaining any phenomenon, meaning physical interpretation, causes. He also goes into semantics, right? He says light bending is, he goes through all these terms that he has, right? And just reading through them, you can see he has no notion whatsoever of scientific language. He says light bending is achromatic. VLBI radio test measured. GR predicts. Radio links measured. Light travel time depends on path geometry. Precise time delays. Events produce curves. Events produce curves. What the hell? Geometric gravity. Geometric gravity? I mean, I just need to know why a pencil falls to the floor. What is this nonsense about geometric gravity? Burst show delays. Photon anti-bunching observed. You observe, like with your eyes, you whole bunch of photons. I've never seen a photon. Please draw one for me, right? Repeatedly observed quantized light. Wavelength is verified. It's always verification. Proving effect. Proving. They prove everything. So you can see his entire language is bogus. All of it. Just these are the statement. This is how he explains things. And he hasn't explained anything. He doesn't realize that none of that has anything to do with an explanation. It's all nonsense. All the words that he put there, all the notions he's got of what physics or science is supposed to be about. Okay, here we have the warped number line fameless. Rejects relativity's warped number lines as nonsense. Obviously, they're saying that, that mass weighs down 4 number lines. Isn't that nonsense, or am I crazy or what? I mean, they're warping time, which we'll talk about this in a minute. But warped number lines, what nonsense is that? Einstein was giving you a description, not an explanation. Einstein could not explain, even to the end of his life, he could not explain how this universe works. He had no idea, no clue whatsoever. He could describe things, with math. So what? That's not science. It's like saying I measured a table and it's 2 meters, 1 micron. I'm very accurately, very precise. And the question is, okay, so what, you get a Nobel for that, for measuring a table? You measured? And they say, well, we measured and found out that the equation fits, the orbit of Mercury, for example, right? So what? That's a description. You get a Nobel for describing that, you've got an equation for the orbit of Mercury. That's just, you can fit any equation in other words, the way it works is it's tautology. You simply fit the equation to match the observation. You don't get make one simpler. I let go of the pencil, it falls to the floor, I measure 1 billion times and find out it's 9.86 meters per second square. Okay, so you get a Nobel for that, for telling me that you measured and you came up with this number, which is based on a preconceived standard. Is that science? Just measuring and putting an equation, a number or whatever? No, again, this is where it always fails. None of this has anything to do with science. Science is using your brain. And using your brain means that you're going to explain something, how this universe works. That's what people want to know out there. That's the type of questions people ask. And so he goes into time dilation. He says, clocks on GPS satellites run faster due to gravitational time dilation. Yeah, they run fast. I don't know how fast my clock runs. I've never seen it run, but I'll put it in the next race that is out there, I guess. This is not an explanation. The fact that one clock runs faster or slower hasn't told me anything about what caused that to happen. And time dilation is a calculation, not a cause. Okay? Time is not a physical object. We're going to find out about that today, right? Time lacks shape. Okay? Have you seen the shape of a second, of an hour, a year? And so it lacks shape. It is irrational to say that a concept dilates. So if it doesn't have shape, how are you going to talk about dilation? Dilation is a word that belongs exclusively to physics. There's no such thing as dilation in mathematics. Okay? So, again, the language is the first thing these people have to take care of. And here's my version of science so that people know where I'm coming from, right? And so we say science, what? Rational explanations. Physics, rational explanations of what? Of causes and mechanisms. Okay, that's what physics is about. And these people say, no, it's about observing, making predictions, writing equations, and describing. No. None of those require that you break your brain. Here's where you got to break your brain, when you have to explain. That's when you have to use your head. And you have all these subdivisions of physics, chemistry, paleontology, biology, etc., right? And you have philosophy is the other branch of science, rational explanations of purposes and reasons, not the nonsense that you find everywhere else, right? And there you see some examples of disciplines that are under philosophy, anthropology, etymology, history, psychiatry, etc., okay? So those are subcategories of philosophy. What do we do here? Well, we do physics. Okay, and what is a physicist? An individual who rationally explains causes and mechanisms underlying phenomena. We have to define what rational and explanations are, right? And we like to define it in the negative, irrational, right? Opposite, antonym, using concepts as objects, which is what mathematical physics does. Okay, so all of mathematics, they use concepts as objects. That's where it all fails. It's an issue of language, primarily. Explaining without defining key words or using them inconsistently. Again, the issue here is language. They use a jargon that makes no sense whatsoever. It's totally irrational. Explanation does not follow from the assumption, right? You have an assumption. I always give the example, the prosecutor presents a knife at the beginning of his explanation or his his version of the events of what happened, and then during the course of his theory he says, and the person died of poisoning. Hold it, you presented a knife and now you're talking about poisoning, right? So that kind of thing. And then unimaginable mechanisms, like you got space-time. Man, is that unimaginable? It's even they admit it. Stephen Hawking admits it's unimaginable. So don't try to imagine this thing that they call space-time. Okay, let me get this out of here. Okay, so let's go with the main course today. What are we going to talk about? Well, we're going to talk about time. But we have a lot of problems with time because it's really gotten out of hand for the last 100 years. We have no idea what time is, but it turns out all these people like Einstein and so on, they have this notion that space-time is something that you warp, these 4 number lines. In fact, they never show you 4 number lines. They always show you 2, and they bend it into a 3rd dimension. That's what they show you, right? And one of those is time, so they warp time and they say that's gravity, what you're staring at there. Okay, so we have a problem there. I like to say space-time is a waste of time, total waste of time. Don't even bother worried about space-time as far as physics is concerned. We don't care what they do in mathematics, but in physics we have no use for space-time or for time for that matter, okay? No use whatsoever for them. Where do we get all this stuff about, time dilation and time travel and twin paradox, all this nonsense that they came up with in the last 100 years, especially Einstein, who try to make sense of all that? It starts with this fellow. His name is Woldemar Voigt, okay? And he came up with this factor, 1 minus v squared over c squared. He's the guy who, as far as I can tell, he's the first guy to come up with that. And so he has this factor, okay, and he was working on the ether. He was trying to explain to some degree, right, again, the null hypothesis, the null results of the Michelson-Morley experiments. They did several. Okay, so he was trying to explain that to some degree, and so he came up with this factor. And there were a couple people. One was Oliver Heaviside, and together with Fitzgerald, another mathematician. And he said, in other words, he was trying to save the ether. He said, no, hold it. Michelson and Morley have to be wrong. There's got to be an ether out there, right? And he said, so what happened? How come he had these null results? And he said, oh, I know. And he says, in order to save the ether and explain the Michelson-Morley results, Oliver Heaviside theorized in 1889 that magnetic fields, he was working more on the electric side, right, deform in the direction of travel. during motion, and that this pancaking, accumulation effect, right, of electromagnetic fields was responsible for the contraction. And so what happened? Well, he talked to Fitzgerald. They talked quite a bit, and they discussed that. And Fitzgerald took that, he borrowed that, and he came up with he didn't come up with a factor. The guy who came up with that was Lorentz, right? He came up with a factor, but they worked it out in such a way that using that factor, they could talk about time dilation. Now, it was time that was, expanding and contracting. And you say, what the hell are they talking about? What do you mean time is expanding and contracting? Is this physics, or or is this the Twilight Zone? What is this all about? And so, they took this. Einstein came a little bit later, and he took this and he came up with this notion that if you put a mass in there, it weighs space-time downwards. And eventually all the mathematicians bought into this. What they were doing is warping the number lines. And the question is, does this make any sense? For a concept known as mass, which is not a physical object, mass weighing down number lines, supposedly 4 number lines, which they replace 3 of them with the word space, and they say, well, this is space, and the other one's time, whatever that means, right? And so they have this, Descartes coordinate system, as they call it, but it's really just number lines. It has nothing to do with dimensions or coordinates or vectors. It's only number lines. They're going to weigh this thing down, which they replace with a net, fish net, trampoline, canvas, whatever you want to call it. And they're going to weigh it down with this concept called mass. So does this make any sense so far in physics? Absolutely not. And it's not my opinion. It's that it's just self-evident. What you're seeing is garbage. That's what you're staring at, just pure unadulterated garbage. Okay, and so what Einie did next, he put the Earth on top and had the moon roll around it. He really did it with the sun and Mercury, right? He wanted to explain the orbit of Mercury. Okay, so this is their notion. This is what we have today. This is the reason this pencil falls. According to them, it's because, the space here is warped. That's why you fall. Because the space underneath me has got a hole in it. That's why I fall. So why do I fall downward? Why don't I fall upwards? They've never explained that. I mean, isn't there space-time upwards also? I'd like to know that. They never draw it upwards. They always, because if they drew it upwards, people would say, well, that's counterintuitive. But if you do it downwards, nobody questions it. That's essentially what it is. And so what's the issue? The issue is none of these people, because it all comes down back to language. The jargon these people have invented, a totally irrational jargon where they have all these concepts such as field and energy, and they just throw them around like, you know what I'm talking about. I'm talking about energy. Oh, yeah, energy, I know that. And nobody has any idea what energy is. And so let's begin there. They have no definitions for any of these words, but they use them liberally like if you knew what they're talking about. Like, you know what I'm talking about, right? No, I don't. Please define. And here you have the first word, energy, and good old Richard Feynman, he comes to the rescue again. He says, it is important to realize that in physics today, we have no knowledge of what energy is. Yeah, and when good old Dickie did not understand, energy is not a what? Energy is a concept. There you have the definition, the ability, the capacity. That's what the word means. So it's defined as a concept. It's not defined as a what, not a thing. And here we have another version of that. Okay, energy is difficult. This is from the AI, by the way. Energy is difficult to define because it is an abstract concept. Yeah, it's a concept rather than a what? Concrete object. And yet, they illustrate it. That's not my illustration at the bottom. I'm just putting that on there. They illustrate it as something like a smoke of some kind that's got rays and blah, blah, blah. Who knows? Very, very impressive images. Is that what energy is? Is that what it looks like? Like, all these lights, all this smoke? Is that what fog, whatever? Well, defined as the capacity to do work, energy is a useful mathematical quantity. It's a quantity, right? But it is not a tangible thing itself. Now, how do you explain this to 99% of the public out there who think that energy is a physical object, partly because they pay for it every month? Yeah, they're not receiving any physical object. They're receiving energy. And what is energy? Well, it's a bill. That's what energy is, just a bill. That's the only tangible part of energy. Okay, and you say, well, but energy runs my lights and my computer. And yeah, again, you need to explain. You need to tell me what energy is, what you think it is, and using that definition, that notion that you just put forth, with that now you have to explain what turns my light on. That's the way it works. You can't just say energy does it. Well, you haven't told me anything. You could have said X, or you could have said, spirit did it. Energy is just another word for spirit. It's a modern spirit, okay? Not the old energy spirit like an angel or a spirit. Now, these are genuine spirits, number spirits. Okay, so here there was a reason. This is a fellow on, this is interesting because this was a fellow on, the Stack Exchange. And he eventually he stopped being a physicist, stopped studying physics because he just couldn't take it any longer. And it's interesting why he quit, and it's got to do with this word field, another famous word of mathematics. There was a reason why I constantly failed physics at school and university, and that reason was that I mentally refused to believe, right, more advanced stuff until I understand the fundamentals, which I eventually never did. Right. One of the most fundamental things in physics that I still don't understand a year after dropping out from the university is the concept of field. No one cared to explain what a field actually is. They just used to throw in a bunch of formulas and everyone was content. And so this is a notion they gave him. I guess he got it out of a book or whatever. It says, an electromagnetic field is a special kind of substance. And it continues, right? And he said, what? A special kind of substance? Are they for real? This sounds like the authors themselves didn't quite understand what a field is, so they decided to throw in a bunch of buzzwords to make it sound right. And I hope you already see why I hate physics. Absolutely, and he's wrong. It's not physics, it's mathematics. If he would have known that what he was doing is not physics, he would have probably been more correct. But here we have what he was told, or where he ended up with this, is a field material. Apparently it isn't. It doesn't consist of particles like my laptop or even the light. Is a field not material but still real? Or it's just a concept that helps us to explain our observations? And his teacher told him a field is a function, right, that returns a value for a point in space. That's what a field is, just a function. A number, a value, etc. I can't understand how mathematical functions can be a part of the universe and shape the reality. Yeah, they're using concepts. And so, what you need to understand is a field is not a physical object. It's a mathematical concept. And it takes a long time for a lot of these people who've been brainwashed to exhaustion to understand that energy and field cannot be used in physics because both of them are concepts. We do not move concepts around in physics. That's okay in poetry, in ordinary speech you can get away with murder. Love moved mountains? Absolutely. And over there, don't say that love moved mountains in physics. Likewise, you can't say field did this and energy did that, not in physics. You can't use those words as physical objects. That's the whole issue. And, 99% of the theories are based on those two words. You can't live without them in mathematical physics. And what are they? Numbers, concepts. Okay, so Einstein gave his best shot at defining the word time, right? Because, again, we don't have a definition for energy. We don't have a definition for field. And no one's got, even to this day, a definition for time. What is time? What is this famous word that we use, that we dilate, that we travel through, that we can go back to the past and come back? When one twin gets older, the other one less older, and so on. What is all this? What is this thing called time that affects us so much? And so Einstein came up with this. He said, in mathematics, he didn't use exactly that word, okay? Time is defined by its measurement. Time is what a clock reads. That's what we get out of the Wikipedia today. Time is what a clock reads, what a clock measures. I don't know. My clock doesn't read anything. I have to read everything myself, the newspaper, all that stuff, because my clock doesn't read. What does a clock read? What are you reading? What are you measuring? And that's what they can't answer. And so to say that it reads X, you can say anything for that matter. And there, you have time travel, all this stuff that they invented today, which has nothing to do with physics. None of this has any reality whatsoever. Okay? Traveling to the past, traveling to the future, which is the same thing, by the way, okay? Because if you can travel to the future, you should be able to travel to the past. And they say, well, we can travel to the future, but not to the past. Well, go ahead and try it. Because it's mentally we can all travel to the past and say, oh, yesterday I talked to Julius Caesar. Oh, okay, you're one of those, huh? Yeah, but so we would treat them like a nut. But traveling to the future, well, we don't have the technology yet. That's what they would tell you. So they can get away with that for quite a while. Okay, so here we have a little more formal definition from the Wikipedia and the dictionary for the word time. What is time? And according to the dictionary, the indefinite continued progress of existence and events in the past, present, and future regarded as a whole. Whatever that means. And what do we see in the Wikipedia? It says, time, the continuous progression of existence that occurs in an apparently irreversible succession. Even that's been overruled. They can now do it in reverse as well, right? Negative time, right? Succession from the past through the present and into the future. So we have to look at these three words that both definitions have. Past, what is it? The set of all events that occurred before a given point in time. Okay, so they use the word time to define past, and they use the word past to define the word time. Love it. Present is the period of time that is occurring now. Okay, what is that? You look at now, the present time. Absolutely love it. So the present is the now, and the now is the present, and both of them are time. Great. What's the future? The time after the past and present. Okay, we learned a lot with all this. Yeah, we have no idea what past, present, and future are because they're defined as time, and time is defined as past, present, and future. Great. So we have synonym, we have circular definitions, and they say, well, you can't define any word precisely because you need words to define words, then you need to define those as well, and those as well, and those as well, ad infinitum. So we have a problem because these people don't understand what a definition is. No one defined what a definition is in the last 10,000 years, right? And that's why we have no definition, no scientific definitions of any value today. That's where the problem is. That's the first thing I had to attack. Definition. We needed to get the language right. If you're going to explain your theory to someone, you should at least have your definitions, down pat. Okay, so here we have one fellow who, because of all this, he concluded something irrational about time dilation. And his name is Don Lincoln. He's from Fermilab, so I guess he's an authority, right? He's on the internet, anyways, and he represents Fermilab, so I guess that's as authoritative as it gets. So listen to Don Lincoln. He'll tell you exactly his version of time dilation. Here it is.
They both agree that the remote person's clock is slower. Observer 2 sees more time elapsed than Observer 1 sees at Observer 1's location, but sees less time elapsed than Observer 1 sees at Observer 2's location. This is a super subtle point, but it clearly says that comparing clocks between two moving observers is a tricky business.
So after 100 years, no one has any idea what time dilation is. Time dilation means that you're standing still and I'm moving, right? Could be at any speed of light, whatever, right? And you say, okay, your time is going slower and my time is going faster. But you're moving with respect to me, right? And so you're going in the opposite direction. Are you moving? Aren't we both moving? And they never figured this out. Einstein especially, he never figured this out. And so let me prove it to you. Here's proof for you. I had a talk with God Almighty himself, the all-powerful man upstairs. I had a talk with him, and we bet a beer, okay? And I said, I can move you. You're not all-powerful. You're not as powerful as you think. You can stand still, whatever, but I'm going to move you. And he said, oh, yeah? And he bet me the beer. And so, so here's good old God, he's up there in the sky, in space. And he said, okay, this is what I'm going to do. I'm going to sit him completely still. And he just pointed and stood there still, completely still. And I had to move him. How was I going to move him? And so I did the following. I just took my little finger out and started moving my finger. And I moved him. And so I said, give me my beer. I won. What do you mean? I stood still and you didn't move me. I said, what do you mean I didn't move you? Look, I can prove it to you. I filmed it, And here it is. Where is it? I missed one. I guess this one's it? Yeah, that one. Sorry. So I showed him that the distance was changing between an atom in my finger and an atom in his big toe. So I proved to him that the distance is changing. And if the distance changes, location changes. And so his toe is moving with respect to my little finger. I moved him. And he finally conceded and, had to give me my beer. I did win that beer fair and square, I was able to move God. And so the question is, if you ever want to prove to someone that you're more powerful than God, he can be all powerful, but he can't stand still if I don't want him to stand still. I'll move my little finger, and he's got no choice but to move with respect to my finger. He changes his distance with respect to it. And this takes us, we need to get through these definitions. This takes us to this. We need this set of definitions to find out what time is. And in objects, that which has shape, space is that which doesn't. Okay, we have the something and the nothing. Okay, they're antonyms. So now we can use these two words consistently. What is distance? Well, it's a separation or space between two objects. Okay, and what is location? It's the set of distances from one object to all the rest in the universe. And now we can define motion, two or more locations of an object. Okay, so now we know what motion is. So if I want to fight God and say, hey, I moved you, all I have to show is that the distance between my little pinky, right, an atom, and his pinky or his chest or his eye or whatever, change distance. If it changed this and changed location, if it changed location, you have two or more locations, you have motion. He moved. I moved you, whether you liked it or not. Okay, so it's done by definitions. We have to respect the definitions, and that's why definitions are very important in science. And so what is time? And we have to disappoint some people out there, because first thing we say is physics has no use for time. We don't use time in physics. Time describes, physics explains. Physics does not have any use for time whatsoever. Time is a measurement. Physics is not about measurement or equations, which are simply descriptions. Okay? We need explanations. And that's why time has no place in physics. The role of physics is to provide physical interpretations for how, meaning why, cause, mechanism, the universe works, causes and mechanisms. Where motion is out there, time is in here. Okay, so time is in your brain. Why? Because time requires memory. Time requires an observer. You can't do without an observer if you're going to talk about time. When there were no humans on Earth, assuming we are the only living entities in the entire universe, when there were no living entities on Earth, there was no such thing as time. All there was motion. Motion was out there. Things were moving. We don't have to have an observer to have motion. Simply have to change location. Time, on the other hand, you need memory. You need to record the previous location of something, the previous motion of another thing, and compare yourself against it. And so time requires someone to make a comparison. What is a comparison? A comparison between two motions. That's what time is. The second hand on, this is an example, the second hand on your watch moves one tick mark while the Earth travels 30 kilometers around the sun. Okay? That's a comparison that a living entity makes. This is just one example. You want to see a cheetah run, you got to compare that motion against something else. For example, if you have the cheetah out there in the universe, or an elephant or whatever running out there, if it's just like that, there's no motion. And you say, well, it's moving its legs. Yeah, but it's moving its legs with what? With respect to the other legs, or with respect to its body. So now you have two things, a motion of a leg versus the motion of another paw or whatever, right? So for there to be no motion whatsoever, the cheetah or whatever animal has to stand completely still, and then there is no motion because you have nothing to compare it with. If the cheetah floats, you wouldn't know it, not in space in the middle of nothingness. The only way is comparing it against something else and say, okay, this is moving this way compared to that one. Now you can start your clock. You can say, well, there's so much motion between them. You record that motion, watch the movie, and you say it moved. And it moved in so much time because I created a standard, the second, the minute, the hour, whatever year. And so, yeah, you need two motions. That's what time is, a comparison of two motions. Okay? Okay, well, I'm going to open the floor up for questions. Give me 10 seconds because it takes about 10 seconds for you to receive my message, 10 seconds to get it back. So if you want to have some questions answered of today's lecture or of anything related to physics, be my guest. Question about light. Going through objects, which you touched upon in a recent broadcast. I am catching up because I haven't watched in a month or so. Okay. What's the question? Going through objects. Okay. And so the question is, but first I have to make sure I got the two versions, yours and your son's. Okay. And he continues, so in the version, the light signaling coming from flame into your eyes is unvaried, whether the wall is there or not. It's just that the presence of the wall adds extra stimuli to the atoms of your eyes, and the sum of these stimuli from the flame and the wall make the wall prevail over the flame in your vision. Whereas your son's version, the signal comes from the atoms of the flame, is being modified itself, and so when it reaches your eyes, it is weaker than what it would be if the wall weren't there. Yeah, we have a difference with my son on that one. My good old son. He went to the States, so I don't have him around here. I'm in Frankfurt. He's in Phoenix. Anyways, the issue is that he's got a different version of of how this works. In my version, the ropes are relayed from atom to atom, okay? And so when they hit an atom on the atom in the wall does not vibrate as much because it's in a rigid structure. The crystal lattice of the wall is a very fixed one, a very strong one. Whereas air, for example, gas or anything like water, they're pushovers. They retransmit it easily. And so that's the difference between, receiving light through a medium like gas or water, a fluid of some kind, or through some kind of rigid object. And then again, you have what we used to call in the semiconductor industry, liquid water, which is glass. Because it's amorphous, okay? And so the issue is, why does it go through glass? Well, again, the glass structure allows for the transfer of, the relay of the signal. And the question is why? How is that one different? And again, we get to the issue that I started the lecture today, which is about what is different about glass that it allows you to bend light and treat it in different ways, right? Why doesn't it go in every direction? Why do we see the colors in a given direction? We see the bending of light, why? And, we don't have an answer for that. We're on record. We don't have an answer for that, for the why light bends sharply. And your question is along those lines. According to my son, he says, instead of the signal going through and being relayed automatically by that atom, the atom kind of stops it. And the signal reaches a brick wall, so to speak, right? So it gets stopped a little bit, right? And so that's why, the light is not transmitted to the other side of the wall. So we have two versions, his version, my version. Again, these are theories. If you have a third one, we'd really appreciate it, but those are our theories for those two. In my case, the signal is transmitted again, but the crystal lattice prevents it from being transmitted the way it should have come in there, right? And in a sense, it's more or less like he says, where you have the signal hitting a brick wall. But again, then you have to explain glass, and you have to explain water and gases. So just be aware of that. There are different variations, and you have to choose your own. Maybe you have a better one, for all we know. Okay, let me go on with the next one. Question on extinction. Okay, I don't see the question. If you have one on extinction, put it on there. Otis Wong says, why does time move forwards? Wrong. Time does not move at all, much less forwards. Time does not have direction. Okay? Time is a number line, and number lines don't have directions. In fact, you can put them in any which way you want. Let's see if I can show you something here, maybe real quick. Give me a second, and I'll show you what I'm talking about. Okay? We're going to show you what time is and why it doesn't move forward. Let's see if I can get it here. Okay. Here's the first one, okay? There's a number line, okay? And you say, that's a number line? Yeah, that's a number line. See, I have all those numbers there. You say, where's the line? Okay, let me see if I can get you the line. Give me a second here. Here's the number line now. Okay, there's the line. Okay, are you happy? You got a line now. Okay, and you say, well, what's the direction of that thing? I mean, which direction is that number line going? And the answer is, the number lines don't have direction. Number lines are numbers. Numbers don't have any direction. They don't have any location. There's no distance between numbers. And here's maybe a summary of that. Okay. Number line does not have direction. Numbers don't have location. Okay. Time is a number line, only magnitudes. And time has no direction. Okay. So, yeah, I mean, time does not have direction, so it doesn't move forward. Forward with respect to what? My forward is not your forward. Your forward's towards me, so, which way does time flow? I mean, can you point to the direction in which time flows? If time flows at all? I mean, how can you talk about the flow of time if time is not a physical object? And again, it's the language that kills us. We have the wrong language. We have an irrational language that the mathematicians have created. And so people think they know what they're talking about. Turns out we have all bogus language, all bogus words, all bogus phrases, and people just repeat them without knowing what they're saying. That's why I had to come down on this language issue. And people say, oh, Bill, you're doing a lot of semantics, philosophy, ontology. No. It's part of the language of physics. That's what it's called. You can't do physics without that language. That's the problem. Okay, let's see. And you talk about how the universe is supposed to sort of blink in and out of existence, as it were, and at a speed we can't comprehend. I'm curious about physics and not an accomplished learner. Okay, what do you mean universe comes in and out of existence? It doesn't. According to the rope model, right, that we have, the universe has always existed, has always been there. In fact, I like to usually do it with this little, if I can get it out of here. This is the entire universe, okay? Okay, that's it. Okay, that's the entire universe. A single thread going around the entire universe, and the thread builds every atom and every rope that interconnects every atom. So all atoms in the universe are physically connected because there is no interruption in the single thread. If we could, or mentally we can, unravel every knot, every atom, and every rope out there, we would end up with a single thread. That's unimaginably big, unimaginably thin, but it's a single thread made of a single piece. Okay, malleable, made of a single piece. That thread is what weaves every atom in the universe and the ropes that interconnect them. Since an object cannot turn into space, because an object is that which has shape and space is that which doesn't have shape, right? An atom cannot convert into empty space, and empty space cannot surreptitiously convert into an atom. We would have to understand or be able to explain the mechanism for that to happen, what caused it to be like that, and nobody can do that. And that's the issue. The universe does not come in and out of existence. It's always been there. The matter in space has always been there. And since space is that which has no shape, has no borders, no limits, no surface, not even God can leave space. So if you believe in God, poor old God is trapped in here. He's just another prisoner, just like us. He cannot leave space. There's nowhere to go because space does not have a border that you can cross. So all the matter that's been here has always been here, okay? And it's just been rolling around all these atoms, all these stars, all these galaxies for gazillions of years. And again, I like to say something that scares some people, so I don't know if you want to turn the TV off right now, but there never was a first human being in the universe. If we go back a million years, a billion years, go back a billion years, we would find a planet somewhere in the universe with life maybe similar to us, okay, human. And if we go a billion years before that, we would find another planet that's got humans in it. And if we go beyond that, another billion years, trillion years, we would find another planet where they had humans somewhere in the universe. And you can go on and on and on and on. And since matter never had a moment of creation, and matter cannot turn into space and space into matter, there was never a first human in the universe. And that blows your mind. Because it's not called infinite, okay, because we're not talking about infinity. It's a wrong word to use. Infinite is an adjective. We don't use it to talk about incessant travel or things related to time, which also have to do with eternity and concepts of that nature. So the correct word is incessant or incessantly. Motion is incessant. That you can talk about. And I'm saying that you can go back in time, if we could, right, incessantly and never find an origin to the universe. If we can't find an origin to the universe, we can't find the first human ever that existed in the universe. Okay, we got it? Okay, why can't I meet my past self? Why can't I meet my past self? And again, I've explained that, and I'm going to have to give you a rain check on that because the explanation involves the Universal movie. And I've explained that. It takes a little more time to explain that. So I'll take that as a rain check, okay? Or you take it as a rain check. I'll answer that question next time. Or please put it in again. I'll tell you why you can't see yourself yesterday, let alone, when you were born. You can't see yourself yesterday. Okay, and I'll show you that. Very simple with a universal movie. Okay, but it's a lengthy explanation. It's good to have the graph of the universal movie. Okay, let's go with another question. If I've done a presentation on the words of physics, I call them the foundations of physics. And they include the word object, the word space, right? Nothing, something and nothing. Includes distance, location, exist, motion, concept, simply because we need to distinguish it between object and concept, right? And I don't know if there's a couple more right off the top of my head. I can't remember another one. But those words are important for physics. If you're going to exist, I hope I mentioned that one. Physics is the science of existence. In order to talk about existence, you have to talk about what's out there. And what's out there, hopefully, is that something is connecting all the atoms, because atoms affect atoms. In the religion of quantum mechanics, they say it's done by magic, that this one affects that one, and there's no mediator. That's known as magic. It's known as black magic. We're saying there is a connection there, a physical connection that we cannot see or touch. That was the solution to that problem. And so, all I'm saying is you need to define these terms, especially the word object and the word exist, because those two belong exclusively to physics. Exist means, an object that has location, and hopefully we know what an object is, which is that which has shape. So you have something, an object that has shape, that which has shape, a word that represents something that has shape. Okay, and you have all these objects, we call them atoms, that make up the universe, and they're all connected. They had better be connected. There had better be a mediator between two atoms, for otherwise we're all crazy. We're saying that there is no mediator, but this ball affects that ball, this object affects that object, with nothing in between. If that ain't magic, I don't know what is. Okay. Fellow says, what are positive and negative ions in the rope model? Well, what they are is clockwise, counterclockwise. Mother Nature does not understand positive, negative, north, south pole. Those are irrelevant terms for Mother Nature. She never went to school. She doesn't know what plus and minus is, subtraction, addition. She doesn't know any of that. She understands objects. She works with objects every day. No one knows it better than her. And so when we're talking about, positive and negative, we're talking about clockwise and counterclockwise motion. That's what it is in physics. Okay? And you can apply that to electricity, magnetism, anything, even the atom, the workings of the atom. Someone says atoms go into and out of existence. No, you cannot go into and out of existence. Okay, let's get rid of that notion. Into and out of existence means that something turned into an object, turned into empty space, into nothing. What is nothing? That which has no shape. Suddenly it lost its shape. It had length, width, and height, and suddenly lost its three dimensions. And it became nothing. No shape. And how do you do it? What's the mechanism? So never talk about coming into existence, going out of existence. That's irrational, because what you're saying is an object turned into empty space turned into an object. That's what you're saying. We cannot rationalize that. Period. We're done. That's how simple it was. There is no extinction, in other words. Humans have always been around. Nothing really becomes extinct. Well, yes and no. Let's put it in the right context. Here on Earth, we have extinction. Okay, we have extinction of dinosaurs, mammal-like reptiles. We have the archosaurs. They became extinct. They're no longer around. Were there archosaurs in some other planet? Absolutely. I'm sure there were in the history of the universe, right? We can go back in time, probably go to some planet somewhere and find that there were archosaurs there. They were alive until they went extinct. Then billions of years later, we invented them, or Mother Nature created them again here on Earth, and they went extinct here as well. And now we have to worry about or go to another planet in the future in a million years or even close by, who knows, for all we know, and we'll find some more archosaurs. Okay, so let's put it in the right context. They become extinct here. Okay? Yeah, humans in that sense were never extinct, but they're going to be extinct very soon here on Earth. we're about to go, all of us. Okay. When I rub my hair to a balloon, why does my hair stand up? Well, because you're not bald. Okay. Standard science says it's the electrons being knocked off from the balloon. So without ions, how does that work? Well, you do have ionization, but we have to understand what ionization is. And again, you're asking questions, very good questions, okay? I'm not saying they're not good questions. The problem is you have to understand what ionization is under the rope model. And right now, I'm just going to explain it. I'll illustrate it next week. But what it is, you have the electron shell moving around. It's spinning. The electron shell spins around itself, the center of the atom, which is the proton star. So it's spinning at great speeds, okay, that electron shell. And it's also pumping back and forth, and the whole atom is also vibrating. All these motions are taking place at the same time, right, constantly. And so the issue with the ionization is you have threads that are moving around, and that atom is now ready to accept any other atom. Because how do we notice that something is ionized? Because it binds with something else, a negative with a positive, right? Which we're saying it's both going clockwise or counterclockwise. And while one comes down, the other one comes up. And that's when they latch onto each other. And that's how these molecules are made. And they're spinning in opposite direction. That's why it's holding onto it physically. Okay, I'll try to illustrate that next week if you remind me. Okay. Yeah, if the quantification of the spinning, I would assume so. I can't really answer that question because, again, it's a question of what's the speed of rotation. I don't know if different atoms have different speeds of rotation. Then you have also the p orbitals, which are different than the s orbitals. S orbitals, they spin in a given, you would say, maybe clockwise or counterclockwise direction from one vantage point of view, right? But then you have the p orbitals, and I would assume they go primarily sideways, which from one angle, again, would be clockwise or counterclockwise, right? But there could be other motions for the p orbitals, the d orbitals, and so on. Each orbital might have a different spin, a different type of spin. Remember, these are balloons. This is what we're talking about. We're talking about a ball of yarn, and it's spinning, but it could be spinning in this direction, right? So there are different ways that an atom might be able to spin, and the question is, how does it bind? And again, the question that this other fellow asked, the ionization, and it's when they go in when they go in the same direction, but as one comes down, the other one comes up, and that's when they latch on, right? I like to use the analogy of the riverboat, the paddle wheels of a riverboat. One paddle wheel comes down, the other one comes up. They're both going in the same direction, right? But as one comes down, the other one comes up, and that's when they hit against each other, right? And they attract. If, on the other hand, they're both going in the opposite directions, they hit each other and push each other away. And that's a mechanism not only for ionization, but also for magnetism. Okay? Can species exist in tandem at the same time? I'm not sure what your question is there. Species, I'm not sure exactly what you're referring to there. You got to clarify that a little more. Yeah, species, I mean, we have lions, or I guess you're saying whether mammals can exist with dinosaurs at the same time. The answer is no. And first of all, the main reason they cannot coexist At least, well, they can and they can't, but we had mammals with the dinosaurs at the same time, right? But the point is, why did the dinosaurs become extinct and the mammals continued? Well, because they were based on different food chains. And so the dinosaurs ate conifers, the mammals ate what we eat today, in other words, flowering plants, seed plants. And so they ate different things. When the food of the dinosaurs went away, they went away, and we continued rolling. So in that sense, yeah, we lived at the same time as the dinosaurs. How far back can we take mammals? Well, certainly we can trace our lineage all the way to the Cambrian. I would think so. I would like to think that, there was some animal, maybe even plant, but some animal in the Cambrian that was our great-great-great-great-grandfather and gave rise eventually to us. All species, all really orders, right, can trace their lineage all the way to the Cambrian, hopefully. Otherwise, how do we get here? Magic wand? My magic wand. Okay. Yeah, one thing, okay, the question is, but how can the shell spin in one direction if there are ropes reaching that atom from all directions? Remember, we have to distinguish between threads and ropes. Rope always remains tight and it's all taut, right? It's pulled tightly between two atoms. It's always taut because every atom in the universe is pulling on every atom in the universe. So right now we have atoms on the other side of the universe that are pulling on every atom of here on Earth. And so that's why they're tight. That's why they're pulled tight always. They're always under tension, no matter what. Because you're talking about gazillions, and even that number seems small, of atoms in the universe, period. It's just countless atoms. And so they're all pulling on each other. So the rope is always tight. Now, how about the threads? The threads are the ones that swing around. And remember the electron shell, the electron membrane, looks something like this. It looks like a ball of yarn, right? It's rolling. That's rolling around the atom at great speeds at the same time that it's pumping and the atom is vibrating, all these motions. But what's happening? Well, let's look at the threads going around. An ionization means one thread or a few threads, pull out, and they are able to latch on to another atom that has the same situation, which is ionized. Ionized simply means a thread has been pulled out, or a few threads have been pulled out. So that atom, let's go simple. If this is the surface of the electron shell of one hydrogen atom, we want it ionized, we have to pull this outwards like so, okay? And that's going to go around. And now because that's going around, you get another hydrogen atom and they bind. But in the case, well, that's a bad example because hydrogen binds covalently, not through, for example, the ionic bond or through the hydrogen bond. But again, we got to look at each specific case. I talked about that a little bit last week, really, about the different kinds of bonds. If you go back there, you'll see the differences between ionic, covalent, metallic bonds, etc. They have different mechanisms, and so you got to look at each one of those mechanisms first. Okay, so let's see. Following the line of thought, humans have always been around. They go extinct here, for example, and arise somewhere else. Yeah. Can there be humans here now in another location in the universe? Yeah, I think they can. You can have humans here, and I'm sure there are humans on some other planet within the universe. But let's look at something, because this is, I think, is important, that what people miss, especially all these people who are wondering about the Fermi paradox. Why haven't the Martians come and visited us, etc.? Or even if they haven't come to us, why haven't we seen life in another planet? Life apparently is a scarce resource. Okay, that's the first thing we have to understand. The second thing we have to understand is to make life it requires, I've got that in my website, it requires very tight conditions, very specific conditions. If we go by the Earth, the only example we have, we have to be at least, third rock from the sun, a certain distance from the sun. It's got to have a certain magnetic field. It's got to have a certain atmosphere, et cetera, et cetera. There maybe the tilt, maybe the magnetism. All these parameters are important because you need to take all of them into consideration to produce life, okay? But that's only the first problem. Let's go to a bigger, much bigger problem, and why Fermi's paradox, I think, is quite easily understood. You have all these people who are looking for life somewhere out there. They're wasting their time. We're never going to find life on another planet in whatever little time we have left. And let me tell you what the problem is. The problem is, when did we invent electricity? And I mean by electricity, inventing electricity, useful electricity. In other words, by using it to, do lights, communicating, with technology that allowed us to send messages, etc. When did we start? Well, we started maybe 150 years ago at the most, right? Maybe 1870s, 1880s. That's when we started using electricity for something useful, began to send signals. Telegraph was a little earlier, but what I'm saying is we only have 150 years of electricity, okay? What do I mean by that? That's not even a drop of water in the ocean of the universe, okay? When you're talking about time-wise, that's nothing. When we're talking about time, 150 years is nothing. It is a lot for us, for me especially, right? But not for the universe. Father Universe, that's not even a drop of water in his ocean. And so what's the issue? Let's assume, we gain consciousness in the Neolithic. We created civilization 5,000, 6,000 years ago. No problem, okay? And another planet is staggered in time behind us. So it's close by, maybe, down the hall, down the street. But it's still in the dinosaur age. Or maybe it's in the, Permian age, mammal-like reptiles or Carboniferous or whatever. So they're still with amphibians over there, and here we are with humans. But we're about to become extinct. We're not going to make it to the 22nd century, no way. And so humans are going to become extinct. And here, these other guys, they have life. They're close by, maybe, in some planet near a star close by. But they can't send a signal because they're in the amphibious stage. By the time they get to the human stage, we're gone. And so on down the line. So there's a question of staggering of time. And I think that's the main factor. For you to be able to send a message to some other civilization, they would have to be born at the same time as us. They more or less had to have a similar history where they're technologically at the same level as we are, and we can send messages to them and them to us. So aside from the fact that it's a scarce resource, life is a scarce resource. We don't see it anywhere in the solar system. Imagine other star systems, most of them are barren, and where there is life, it's not at the same level as we are. And the level in which we can send and receive messages is only 150, maybe 200 years, and then we're gone. And then another civilization pops up, they have humans, and they say, where'd all the humans go? Fermi's paradox in another planet. So it's a question of staggering of time, okay, primarily. That's the number one issue. Okay. I like that one. Is there a mechanism that explains how humans can always exist somewhere in the universe? How does the rote model explain the same species, humans, tigers, coming to be perpetually? No, not perpetual. Humans are not perpetual. Life is not perpetual. There's going to be a total extinction event eventually on Earth where no life, not even plants, exist anymore. And that's farther down the road. We're not going to see it because we're going to become extinct a lot earlier. But the rope has really nothing to do with that. In other words, the rope has to do with light, with gravity, that kind of thing, but not with the extinction of man. Even though paleontology is a branch of physics, but it's a special branch of physics dealing with living entities and what causes them to go extinct. Paleontology is a discipline that deals with death. Okay, they are medical examiners, detectives that go out there and look for clues on what made the animals and the plants in the past disappear. And so, yeah, that's their job. That's what a paleontologist really has to do. Once we know extinction, we're done with paleontology. They can continue classifying animals and plants all they want, but we got the answer we want, which is the cause of extinction. So, and to say that, humans will forever live or that life will forever live on our planet, no. Will life exist always in the universe? Yes. In fact, there's very likely life at this same time, right? And again, within one frame of the Universal movie, not garbage from Relativity, this stuff that their time is different than our time. No, there's a single time in the universe, which is the present, and it's what you see in a single frame of the Universal movie. And God knows that. He's all powerful, he's all knowing. He looks at that frame, he says, I took a snapshot, and here we have a human here in this planet, another human here in that planet, another human there in another planet. Okay, and I'm sure there are planets in the universe at this moment in time that, cross-section of time, cross-section of motion, location, that you'll find humans somewhere in the universe. But they're so far apart from each other, and again, there's this issue of staggering of time that I don't think we can ever see another human. There's no way. No way whatsoever. The statistics are against it, probabilities. Frank Bray's point is that since the threads are spinning perpendicular to the ropes, okay, wouldn't they clash against the ropes and hence be unable to move 360? Well, remember, there's no touch. The Mother Nature's touch, that's why we have to define touch. And I define that in my book. Everybody... And I don't just give the definition because you say, well, where'd you get that? You got to go and read the justification for the definition. But we have a definition of the word touch. And, the threads, for our macro world, they don't touch. Okay? So ropes don't touch with threads or vice versa. They go right through each other. And you say, well, how can that be? Yeah, it's very hard to explain for us because we're used to our universe, our macro world, where, ropes don't go through ropes, threads don't go through threads, sewing threads don't go through sewing threads. And you say, how can that be in Mother Nature's universe and still maintain, the tightness? And one way you can look at it, again, this is the way to imagine it, to visualize it. You have a thread going through a rope or through another thread, or a rope through rope, it doesn't really matter. And think of it as water going through water, okay? Can water go through water? Yeah, water can go through water because momentarily they blend. You have all these water particles and they're all there, right? A given region, and then like if you take two hoses and just run them through each other, they'll go through each other. And you say, well, how can that be? Atoms don't go through each other, and they don't. In our macro world, all those water molecules, each one has a different location, and they didn't really go through each other, right? But again, we have situations like neutron bombardment, and you have good old Rutherford there, and he says, it went right through. How can that be? How did matter go through matter? How do neutrinos go through atoms or whatever? You say, hold it, that's matter. Yeah, it interacts weakly with matter. That's the way they explain it. Okay, so we have the same situation. Mother Nature runs a very weird universe at her level that we cannot easily comprehend at our macro level. We have to sacrifice some misconceptions that we have about how she runs her world, and part of that is the touch issue. And again, before you can go through, you must touch. Okay, if I want to go through my table, hopefully at some point I touch it. And so you first need to define touch before you explain going through. Okay, so it's a tricky one. Okay, okay. Touch is when two objects become one, right? Yeah, in other words, there is no space between them. But again, you have to understand what with the context here, and this is important. If you talk about a table, right, you say, well, does a table touch another table? Does a chair touch the table? And as long as there's space in there, and there is, they haven't touched. For the first purposes of physics, not for the purposes of ordinary speech. Okay, ordinary speech, we say the chair touched the table, no problem. In physics, we cannot say that. We cannot say that because there's distance, there's space between the chair and the table, unless they merge. But what's got to merge? Okay, so now we have to take the microscope and look to see if they touch. What does touch mean? Well, they have to blend. But what blends? Not the table. Now we can no longer talk about table and chair. Now we have to talk about atoms blending. It's at that level, because in order to talk about zero distance or zero space between them, right? So now you have surface to surface, one atom touching another one. When a hydrogen blends with another hydrogen, forms a figure eight, I think they touched because now they merged. Okay? They formed one object called a hydrogen molecule, H2, right? But even there we have a problem, because are we saying that the threads that form the shell of one atom melted and blended with the shell, with the threads of another atom? Did they blend? Or are they side by side? So very tricky, and you got to get to that level in order to talk about touch for the purposes of physics. Okay, very important. Okay? It's a qualitative concept, this touch thing. Math has no say in this whatsoever. Okay. I meant perpetual humans in the sense of the universe, not on just our planet. I'm saying that humans will always be perpetual. We're perpetual. We go back in time, we won't find the first human. If we could go to the future, right, we would find humans all the time, because the universe continues on forever. There is no stop to the universe. The matter in the universe has nowhere to leave space, because there is nowhere surrounding space. There is no border, there is no surface. So matter cannot leave space. It's trapped within space. And within that, matter cannot convert into space, space into matter. That means matter has always been there. And if it's always been there, and we go back in time, we will find stars and universes and different universes and galaxies and atoms and gases and so on. And we go further back in time, we'll find the same thing all over, forever. And that means that if we humans were made here on Earth by some kind of chemical and physical process, if we go back in time, well, for sure, with so many gazillions of planets and stars in the universe, we're going to find humans as well. Not only today, if we could go to the other side of the universe, but if we go into the past, if we could time travel, we would find humans a million years, gazillions of years in the past. There was never a first human. And if we could go to the future, which hasn't happened yet, we would also find, humans somewhere on the universe. It's somewhere in a planet, somewhere in the universe. And it's both ways, it's just a nonstop, it's, what do you call it? Perpetual motion. Okay. Okay. Long question time. Cheers, folks. Okay. We'll see you next time. Bye-bye.